So again, how do you measure rate? So this is going to be a little less theoretical, and then we're actually going to do kind of a fun example. I do have a lab planned for you, and in a person live lab, but you're going to do it wherever you want. So I'll talk about that in a little bit. It's going to be a home project. So how do we measure rate, right? The way we measure rate is we have to quantify something. So I'm going to have, let's say, concentration 1, right? I'll measure this at time 1. So this is concentration. And again, this is always, time is always what we're measuring against. So let's say it's the initial concentration, and that's usually pretty easy to measure or even to calculate in a lot of instances. We just make the solution so we know the concentration. But oftentimes we measure it, and a lot of times it's using color as the measurement tool. And that's unfortunately what we would have done in lab, but anyways. So you have the concentration at some time, and let's say we'll call that T1, and we'll call that concentration C1. And then in order to get the rate, you need to know how fast the concentration changes. So then you would measure a C2 at a time T2, like that, okay? And this is in fact how you measure any rate. A quantity at one time and a quantity at another time, and then you can calculate rate. So how do I calculate it? Rate, okay, and again, how fast it's going, right, is measured from the concentration change. So where I'm going to do this, it's the change in concentration over the change in time, like that. Now, whenever we do, oops, okay. Whenever we do delta, right, this is final minus initial. So like remember doing delta H, right? It was always products minus reactions because products is final and reactants is initial. That's why we get delta H. Okay, so it's always products minus reactants, final minus initial. So that means I'm going to go C2, right, minus C1. That's the change over T2 minus T1. And that's how you calculate it. Now, of course, we're going to do it with some data, and I'm going to make it kind of fun. I found this cool video. I don't know if we'll watch the whole thing, but I found this kind of fun video that we can calculate a rate of. Because it was one of those things I didn't know and I wanted to know, right? But I want you to think about this too. Where have you seen this kind of formula before, right? And maybe it's kind of familiar to you. Where you see it is math. Where you see it is a math class. And in a math class, you have a curve that looks like this, let's say, and you want to know the slope, right? Well, probably this is not the best example to use, but let's say the curve looks like this. Then what you're going to do is you're going to go like this. You're going to take 2 points on the line. Now, this line might be actually for some data, but you drew a straight line through it, right? And then what you're going to do is you're going to take x1 and x2 and y1, because that goes with x1 and y2, and then you're going to calculate the slope. And that's going to be delta y over delta x, and that's going to be, right, y2 minus y1 over x2 minus x1. Now, in this case, right, I used x's, but in our example, it was time, right? And in this case, you know that the slope will be negative because the line is going down, and y2, I don't know what I did here. This y2 doesn't belong there. It belongs here. And this is y1. I don't know what I'm on something. I don't know. Yeah. So I was using the point on the corner of the thing I drew. That doesn't count. It's the line. So it's x. It's y, because y2 is below y1. This is where I wanted to go with this. it's a negative slope, because when you subtract those, it'll be negative, and that's why we have negative slopes for the lines that are going downward. Okay? Okay, now, here's the fun one. Hopefully this will work. I'm going to pause the video and save some stuff real quick, and then I'll restart here. You won't see, hopefully, anything bad happen here. So I realized that you weren't able to hear the system sound in those videos, so I'll try and post those for you to see. So here's what we're going to do. We're going to watch a little video, and we're going to calculate the velocity. Okay, so it's like doing a reaction rate, except for velocities are nice because you can see where things are. And this is kind of a fun one. Let's see if I can get this to start. All right, so here we go. So this is a garden slug that you can see right here on the screen, I hope. And we're going to make him move. Now, let's say we want to measure how fast he's going. But, you know, it's a slug. So let me back up a little bit, and let's see if we can start him right at 3 inches. Okay. So let's see where he goes here. So that's at 3, let's say that's at 3 inches, kind of looking right here. At the time is 21.79 seconds. So what I'm going to do is I'm going to go ahead and write that down. I wrote it down, and that's at 3 inches. So he's at 3 inches. So we'll call that 3.0 because I'm pretty sure it's pretty close to being at the 3-inch mark, and it's 21.79 seconds. And now we're going to let him travel. And of course, you know, this is not in real time. This is kind of a recorded video, and then they sped it up. But they go pretty fast. I actually didn't realize they could travel this fast. It's probably heading for my tomatoes or something. I don't know. By the way, they have burrows, and they travel in the same path all the time. So let's say I'm going to stop them right at the 7. There you go. Right a little bit. Yeah, let's call that a little bit past where I wanted to go. Yeah, that's closer. That's closer to 7. Okay, so we're going to call that 7 inches, 7.0 inches. And oftentimes you'll do this on your data. You'll look for spots in your data where it's easy to measure. And that's 2 minutes and, well, 0.96 seconds. Okay, so let's go ahead and go back to our lecture and plug those numbers in. All right, so let's see. How do I have this organized? I have time on the right, and I have x, the distance, on the left. So for time 1, I have 21.79 seconds, and then I have 2 minutes and 0.96 seconds. Okay, and then let's see, what else do we have here? Oh, I have the distances. That's 3.0 and 7.0, and these are in inches. That was an inch ruler. Okay, so we got the numbers we need. So what we're going to do is we're going to calculate the rate of velocity. You would do the same things with concentrations, and then we'll find out how fast the slug goes, because this is one of those things I kind of wanted to know. So what is the equation, right? So the equation would be rate, right, is delta t, or delta x over delta t. That's what I'm dealing with here. And then I'll have 7.0 minus 3.0 inches, right? And then at the bottom, what am I going to put, right? Well, T2 is 2 minutes, so that's 120, right? So again, sorry, my units. These units have to match, just like in any other problem. Units have to match. So I'm going to 120.96 seconds minus 21.79 seconds, like that. And then I can plug it into my handy dandy calculator, which is the calculator I hate, but it's always the one I have on hand. I hate this thing. Oh, so we're going to go 7 minus 3. So if you'll forgive me, I'm not going to use the calculator for that one. That's 4. And then I probably don't need to use the calculator for the other one, but I'm going to, just because I know I'll screw it up. So now it's going to be 120.96 minus 21.79, 21.79. Okay, and then that'll give me 99.17. Okay, so 99 seconds like this. So now I could do the rest of the math. It's going to be 4 divided by 99.17, and that comes out to be, hang on, I got to move these. The controllers for the recording always go to the bottom of the screen, right where I put my hand, and so I've always got to move it out of the way, or I'll shut it off by accident. So, oh, sorry, that's going to be, let's see, 0.0403. And the units are inches per second, like that. And then, the whole sig fig thing, there's only 2 sig figs there, so I'm going to call this 4.0 times 10 to the minus 3 inches per second. It's not really fast, right? They do actually have a race I think it's in England somewhere, it's a snail race, and they put snails on a circular racing track, and they put little helmets on them and everything. It's really cute. Anyways, yeah. I probably, just by saying that, have wasted like an hour of your life later. Sorry. Okay, so that's what happened when I did this. I'm like, oh, look at that. And I started watching videos about slugs. All right. So here's some just general ideas about reaction rates as they relate to reactions. Okay. First is the concentration of reactants is always the highest at the start of the reaction. And I think that makes sense. But as the reaction goes, right, the reactants are used up, and so their concentrations drop off. And because concentration is an important part of how fast a reaction goes, the rate slows down. Right, now think about what that means, like in a graph, because I actually haven't shown you like a real graph yet. Right, what does that mean? Well, the slope, if the rate's the highest at the start, that means the slope will be the highest at the start. Like, I don't know how I can make, yeah, well, slight slope will be highest at the start. Maybe it looks better that way for you. I don't know. I can't tell which way it looks best to you, honestly. The highest at the start, and then over time as it goes, it's going to go lower and lower. It probably won't drop to 0, actually, although it might not be measurable changes, but in theory, reactions slow down over time. They just keep getting slower and slower and slower, just because the concentration goes down. Now, that's not always the case, but it is generally the case that you see that, okay? Now, the other thing to think about is as the reaction goes, you begin to make product. So every bit of reactant that gets used up, right, begins to generate product. So in principle, even though we're talking about reactants getting used up during the course of the reaction, oftentimes it's the product that we measure, because the product starts out at 0, and it turns out 0 is really easy to measure. It's just 0, right? And then it increases over time, and so you can measure the products coming out as well as the reactants going down as a way of measuring the reaction rate. Okay, so a little bit of like background. Again, this is how you would do the average versus the instantaneous rate. This is just a nicer slide, right? So this graph is showing 2 measurements of the instantaneous rate. So what they did, and this is honestly not what I would have done, but what they did was they drew a tangent line. This is my tangent line. This is from your book. And on the curve to this point, because this is where they wanted to measure the instantaneous rate of the reaction, and then they drew this line, and then they measured the rise and the run, right? So this red line is for the product that's formed, and this green line is for the reactant. And I know that because You can look in your book. There's a reaction right there. I know that because there's the reaction right there. But I also know that because the reactants go down generally, the products go up. So if I wanted to calculate the reaction rate, okay, or the rate, sorry, not the reaction rate. Oh yeah, that all says reaction rate. I'll have to change that. But if this should just say rate, get rid of the reaction. Turns out the reaction rate and the rate aren't always the same. So if I want to calculate the rate, and this is the instantaneous rate, I would say rate equals, and then they calculated these parts for me. So this is going to be, oh, I'm going to do this one down here. Negative 0.28, right, like that. And then it's divided by, and then they did it for 40 seconds. They measured that out as 40 seconds. And the units on this axis are molarity, so it's like that. And so the rate comes out to be 0.28 divided by 40. And that'll come out to be like 7.0 times 10 to the minus third. And they got a negative sign here. And the negative just means it's going down, okay? Now, let's do the calculation for the HI, right? So this is the rate for, I think it was H2, yeah, H2. We're going to do the rate for HI. So that's going to be, again, measuring 0.56, right? And then that's units of molarity. And then I'm going to do, what is it, 40 seconds again. And you notice that it's 0.56 positive because it's increasing, right? And so that's going to come out to 1.4 times 10 to the minus 2. And I'm guessing, let's go ahead and pull the calculator out, and I'll tell you why I think it's that in a second. So that's going to be 0.56, so 0.56 divided by 40. Yeah, 1.4 times 10 to the minus 2. I just did the scientific notation conversion in my head. The units for both of these are in molarities per second. Molarities per second. Okay, good. All right, so this is how we measure rate. The instantaneous rate is used by taking a tangent line. If you wanted the average rate, then what you would do is you would take the slope between 2 points. So you would actually use, let's say, those 2 data points and calculate that. And I'll show you how to do that on another set of data. Okay, so let's talk about this a little bit. Why are the numbers different? Well, they're different because of stoichiometry, right? There's a 2 here. And the HI gets produced twice as fast as the H2 gets used. And the result is, right, the slope is twice as big. You could see that, that's minus 2. You could see that really easy if you just wrote this as 10 to the minus third here. So I'll do 10 to the minus third, which means I have to shift it over to the right. So it's going to be 14 times 10 to the minus third molarities per second. And now that I have them in the same exponential scientific notation, you can see 14 is twice 7. So it's going twice as fast just because the stoichiometry dictates that it would go twice as fast. All right, so this is just some examples, and the data's on the next slide, but I figured I just leave that on the next slide. Originally, it was in front of the graph, but I think you don't need to see the data actually to do this. Okay, so this is average rate calculation. I forgot to put that on the slide, average rate. And what's the average, how the average rate is calculated that's different than the instantaneous rate is you just use the data points. So you'll see in this, well, maybe you do need to see the data. For A, the concentration is 1 millimolar, so that's 1 times 10 to the minus third molar, and then 0.74 millimolar, right? So to calculate the rate, it's 0.74 millimolar minus 1 millimolar divided by the change in time. And so your change in time is 0 to 10, so it goes from 10 seconds minus 0. So this is concentration 2 and this is concentration 1, this is T2, and this is T1, and this is the rate that you get, right? And then over time, right, we're going to calculate, so this is the initial rate, and then we're going to calculate this final rate, and the final rate is just the last 2 data points. It's crazy how many people struggle with just terms in here, just because, and if it wasn't that it was kinetics, you'd be like, oh yeah, of course that's what that is. But for some reason in kinetics, there's so many terms that are thrown at you that are new. When somebody says just measure the initial rate, you're like, what's that, right? Anyways, it's the initial rate. It's the first 2 data points. The final rate would be the last 2 data points, right? Anyways, what you're going to do then is calculate. You'll get negative 2.6 times 10 to the minus 5th, right? And then if you go down here and you recalculate the rate, this is after 60 seconds, somewhere between 50 and 60 seconds. It's negative 6 times 10 to the minus 6. So it's actually a smaller number. And in a sense, you can just see it here. The slope is steeper here than it is here. And that's a result of the rate of the reaction going down as the concentration goes down. So that's why the little notes there, it's kind of a giant note. The concentration can affect rate. And this is a graph showing how you measure average rate. If you wanted to calculate other rates from this data, let's say example you want to do for B, all the data for B is here for you to do that calculation, okay? And if you try it and you're not sure if you're doing it right, just ask me and I'll help you out with that. Okay, so let's move on here. This is kind of a newish topic. Maybe I should start a new recording, but I'll just leave it go for now. There's a thing called the rate, right? That thing that's called the rate is what we've been looking at, the change in concentration over the change in time. And then there's this thing called the reaction rate. And it is so easy to mix those up. Okay, so you got to be really, really good with your definitions and thinking like, oh, I need to do rate, that means slope, right? Rise over run. Delta A over delta T, or delta Y over delta T, that kind of thing. Reaction rate actually takes into account stoichiometry. So let's see if I can do this the right way. Okay, and I will point out that reaction rate, I use the letters RR so people don't get it confused, but I'll say reaction rate. But when I write it, I always write RR. And that's a habit I started getting into in the last, I don't know, half dozen years or so, just to keep it straight for students, okay? I don't actually know of any book that uses RR for reaction rate, but if you can use that term RR, it'll help you keep things straight, okay? So reaction rate incorporates stoichiometry. So let me give you sort of a sample reaction. Let's say A plus 2B, let's do 2A plus B makes 3C, like that, right? And let's say I measure the concentration change of B, right? Well, B will be going down at a rate of delta B over delta T, like that. That'll be its rate. Now, A will be going delta, oh gosh, A is a horrible letter for this because it looks like a delta. Delta A over delta T, like this. And you know, because there's a 2 here, right, it's going to be going twice as fast because 2 A's get used for every B, and 3 C's will be going, the C's will be going even faster, but in the upward direction. Here's the thing. When we're talking about reaction rate, okay, we're talking about this arrow. How fast is the arrow going? Well, B pretty closely reflects how fast the reaction arrow is going. That is, how fast are 2 A's and a B getting together, right? And the way you do that is this. You incorporate the stoichiometry by normalizing to the coefficient, okay? So normalizing in math just means really dividing. So I have B, right? Change in B, oh sorry, reaction rate is going to be the change, right? Oh, sorry, and I'll call that RR is equal to 1 over 1, and then I'm going to use a negative sign, and then it's going to be delta B over delta t, like that. So what is this 1 over 1? This is the coefficient for b. Okay. The other one is just a 1 from being the reciprocal of b. So you're taking the reciprocal of the coefficient and multiplying it. Another way to look at this is RR is equal to minus 1 over 1 times the rate. And that's how reaction rate and rate are different. Okay, so you're thinking to yourself, well, you didn't do anything, right? In this case, I didn't. What I did, though, is I made it a positive number, okay? Because we want reaction rates always to be reflecting a positive number, because when you're measuring these reactions, they're never going backwards, they're always going forwards. And so it's positive, the direction of the reaction is positive, so we take into account that the reactants are always going down in the reaction rate by introducing that negative sign. So, having said that, if I wanted to calculate, oh, let me write this, the rate of B, like this. If I wanted to do the same calculation from A, then I could say reaction rate, right, is equal to negative, because that's to make it positive, right, 1 over A, or 2, sorry, and this is delta A over delta T. In other words, it's equal to 1/2, change the sign, rate of A, like that, okay? Now, we have some data that we can actually look at, it turns out. So we're going to go back. And it's this data here. And, right, this is the rate of H2. And this is the rate of HI. So if I want to calculate the reaction rate, and this is over, and they're both at the same point in time. If I want to calculate the reaction rate, right, that from HI, for example, that'd be minus, and you'll notice it has a 2 here. Well, sorry, and it's a plus. So it's 1 over 2 times, and then it's 1.4 times 10 to the minus 2. And that becomes 7.0 times 10 to the minus 3. Like that. I just divided that number by 2. Now, if I'm going to do the same thing with this data, right, then what I'm going to do is I'm going to say the reaction rate is equal to, right, minus 1 over 1 times, should have made the slide bigger. Sorry, didn't realize it was going to get so crowded. Times negative, right, 7.0 times 10 to the minus third. And that's going to be 7.0 times 10 to the minus third. And what you should notice, right, is that these numbers are the same. Because the reaction rate is referring to how fast the reaction's going. So they should all be the same at the same time, right? Because we're all measuring it for one reaction. They're all being used or being produced in the same reaction. And that's the reason why we do the negative sign for the reactants and we divide by the stoichiometric coefficients. In essence, you're just trying to see how fast the reaction arrow is moving. All right, so this is your chance to try this out on your own. So this is how I usually do this. I will show you the problem. I'll pause on my end and fill it all out. And you should pause it on your end and try to figure out how you're going to do that, okay, how you're going to do the calculation. And then when you start it again, I'll have the answer for one problem, and then we'll pause and do the same thing for the next problem, okay? So this is where I pause it, this is where you pause it, and then when you start it up again, you should see the answers. All right, there it is. So it's asking for the reaction rate, and so I took the 3, right? That's the coefficient for A, and I divided by 3, took the negative sign, multiplied by the rate for A. That's what this number is here, right? So that's what gives me this part that's right here. Now, do the math, get this, do the math, get that. So this is the reaction rate. Now, this is this doesn't have the time specified, right? So these don't have to match. So don't worry, like if you try to do the second one and you don't get the same answer. I didn't say when these were measured. And so you don't have to get the same answer for them. So this is, again, hopefully that's what you got. Again, I'll pause it and let's see what you get for the next question. Okay, that's what you should have gotten for the second one. Let me make sure I'm recording the right screen. That's what I got for the second one. And basically, because it's a product, it's a positive, so I don't need to change the sign, right? And I'm only dividing by 2 because that's its coefficient, so that gives you the answer. So hopefully you got those. So let's bend your brain a little bit. How do you do this one? I'm going to actually pause it and let you think about this for a little bit, and then we'll talk it through. I'll have some notes written up, right, about how you would solve this problem. It says the rate for A, right, not reaction rate, the rate for A is this. What's the rate for C at that time? Okay, so I'll pause it and then I'll have some relationships drawn out, and then we can talk about how you do these problems. All right, so these are the little notes I meant to put up there. I also noticed that when I was typing this out, the negative sign got left out, so I put that in there. So this is how I do it. The reaction rate is equal to 1/3 times the rate for A, and it's equal to 1/2 times the rate of C. So now what you have is you can solve these two. Okay. So when you do that, what you're going to have is the rate for C. So that's delta C over delta T. That's what we're looking for. That's going to be negative 2/3 times the rate for A, like that. Now, some of you may pick up on this and may have already seen it. All I'm really doing here is stoichiometry, right? So let's say it had 1 mole of A, and I wanted to convert it over to moles of C, right? Well, in order to get it over to moles of C, what I'm going to do is say, well, I need 3 moles of A for every 2 moles of C. Like that. And that's where that 2/3 comes from. It's actually, when you do this kind of particular problem, it's a mole conversion between one reactant and one product, or 2 reactants. And so when all else fails, right, you can just sort of rely on the stoichiometry. The only thing you can't pick up on this is that negative sign. The negative sign is part of this equation. But if you can remember that reaction rates are always positive, you can make that go away. Just saying. Okay. I just want you to be confident in yourself that way. So anyways, I'll go ahead and do this calculation. So it's negative 2/3 times negative 0.0150 molarity units per second, like this. And that ends up being 0.0100 molarity units per second, like that. I picked numbers that I could do the math in my head, so hopefully I did it right. Okay, there you go. So that's it for this segment. I'm gonna stop and see what's next. So this last segment of rates and reaction rates, I just wanted to give this sort of general formula. You'll see this in your book or something similar to this in your book. I always thought this was sort of the non-intuitive here's an equation and beat yourself up with it approach. But anyways, here's an equation, so beat yourself up with it. The reaction rate for the reactants can be written like this. So what does this mean? If I have a reaction whose coefficient is W, right, and then the reactant is A, to write the reaction rate from that, I would say minus, because it's a reactant, 1/W, that's the coefficient, times the change for A, or I could do it for B. Now, it's true for the products, right, that I could write 1/Y for C, because that's its coefficient, and I don't put the negative sign in there because delta C is already positive. And then I could do the same thing for D, and if I need to solve for, let's say, A from D, all I have to do is set these two equal to each other because these are the same. Okay, so anyways, yeah, I hope that you enjoyed that. So, so that's it for this segment. Next we'll go and we're going to be talking about rate laws, okay? All right, so the next thing that we're talking about is rate laws. So we've talked about calculating rates, right? So what do we do with those? I mean, what's the purpose of calculating rates? And the actually answer is to make these things that we call rate laws. A rate law just gives us the relationship between the concentration and how fast a reaction will go. So think about what we've been doing. We've been measuring concentrations and seeing how they change with time, right? Or and so now what we're going to do is look at how the concentration can be used to predict the reaction rate. Okay, so uh, what do they look like? Well, let's say this is our reaction that's right here, right? A plus 2B goes to 3C. A rate law might look, for example, like this. So this reaction rate, right, is equal to K times the concentration of, let's say, A times B. It might look like that. And so there are different parts to the equation. There's the reaction rates, right? RR is still the reaction rate, not rate. There's, there's these brackets like this, right? Like this is the concentration A. And then there's brackets like this. That's concentration B. But then there's this K, and this is known as the rate constant. It's the proportionality constant. Because you can always say the rate is proportional to A, and the rate is proportional to B, or rate is proportional to A times B. You can say stuff like that. Remember, if you're going to make it an equality, then typically throw in a proportionality constant. And so in this case, K is that value, rate constant. Now, here's the deal. There are some common, some mathematical forms that we have for rate laws, because it turns out, like the one that I did for you here, this is kind of this sort of hopefully the simplest one. Kind of turns out there's possibilities that it looks like this. And I'm going to get rid of I'm going to drop the brackets so I don't have to draw them all. It could look like that. And so now this, right, is used to represent that. And that's just a simplifying thing to make it go a little faster for us. Or it could look like this. Let's do B instead. And remember, this would be b to the first, right? So we haven't said that, but there's implied ones on these. Because if they were zeros, right, anything raised to the 0 power, let's say I take a to the 0 power, anything raised to the 0 power is 1. Okay, so having said that, how do you know which one it is, right? How do you know what the relationship is? And the actual answer just comes down to this. You have to do an experiment. In order to figure out what the orders are, okay, figuring out the orders. Remember, those orders, this is the powers, right? In order to figure those out, you just have to do an experiment and find out. And so we call these, like part of the different parts, right? Like the exponents are called orders, just like they are in math. So we're looking for the reactant orders or the reaction orders in order to figure out what the rate law is. And so we could say they're 0 order. That means something, right? First order is what I'm showing you here. And then second order is what I'm showing you for, oh gosh, how did I do that? The second order is what I'm showing you for here. Now, when we say something is 0 order, simply that means, right, its concentration, regardless of what it is, doesn't affect the rate of the reaction. That's a 0 order reactant. So the common ones, it turns out the orders are 0, 1, and 2, but you can have halves. Like you can have a half order, you can have a 1.5 order, you can have a 2/3 order, you can have fractions like that too. We will not encounter any of the weird fractions, but a half maybe you'll occasionally run into. So these are what rate laws are, and we determine them experimentally, okay? So, just some important ideas before we get into the calculations. The rate laws are always determined from data. The type of data that we usually use are called initial rate data. So remember when I talked about initial rate data, initial rate um, for a reaction earlier? We put the reactants in, we start the reaction, often by mixing, and then we look to see what that initial concentration change is over time. Okay, and so we usually change the initial concentration, and we measure the rate at one concentration, and then we change the concentration, and then we remeasure the rate. Okay, so we do this to get the orders, but the idea is you have to change the concentration and measure the rate change, right, in order to figure out what the order is. And basically, it's lather, rinse, repeat. You know the thing it says on a shampoo bottle, right? Um, if you have two reactants, you got to do at least 2 experiments for each. Well, actually, you can get away with fewer than that. But let's say if you have 2 reactants, then you would need 4 experiments. That's kind of the simple way to think about it. If you had 4 reactants, then you have to do 8 experiments. So these things are all interrelated, but the easiest way to do these experiments is leave one concentration the same at the beginning of the reaction and then change the concentration of another. And then you can see very clearly what that one reactant is doing. Okay? So we can use this change. It's really like the ratio of the reaction rate change versus concentration change to figure out what the orders are in the rate law. So let's take, and I think, yeah, I used to show all the work on the slide, but I think it's easier for me to explain it if I don't do it that way. And I'll use some different colors to help you, but here's what we're going to do. We want to figure out how the rate changes for A. Okay, so how are we going to do that? Well, clearly you have to change the concentration for A, right? So if you're looking at this data here, right, you have 3 experiments. This is like the bare minimum number of experiments. Like I said, there would be 4 for 2, but the bare minimum is actually 3, and you'll see how we do this. Which experiments does A change in? So the way this is set up, right, is for experiments 1 and 3. And then the other thing that needs to be true is these are equal. Does that make sense, right? That way I'm only looking at the change in one variable. Now this is my initial reaction rate over here. So in order to get the rate law, and I'm going to show you 2 ways to do this. I have a favorite way to do it, and then I have the way that I'm supposed to teach it, so I'll show you that first. Anyways, so what we're going to do is we're going to say for reaction rate, right, 3, and I'm doing 3 over 1 because if you notice this, the way I type these out, it shows up that 16 is bigger than 4. So I'm going to do reaction rate 3 over reaction rate 1. Okay, so that's going to be 16.0 times 10 to the minus 5, and then 4.0 times 10 to the minus 5. And then this is what I'm going to do, right? I'm going to say it like this. This is equal to, I maybe should show you something else first, but I'll just show you what it's equal to. It's equal to this. And I'm cheating. This is the way I like to do it and not the way the book does it. This is the concentration for reaction rate of A, for reaction rate 3, right? And then for reaction rate 1, the concentration is 0.100. And this is going to be raised to a power n. That's what I'm trying to determine, what that power n is. Okay, so then I'm going to take and I'll divide this out, and this will come out to be 4.0 is equal to 2 to the n. Now, here's the tricky thing. You have to figure out what n is. Now, in this case, you could probably figure it out just by looking at it. Like, what's the exponent of 2 that gives you 4? And it turns out that that's 2, right? So n is equal to 2 in this case. So we've just figured out what the order is for A. So I know that my reaction rate law, okay, is going to be K times A to the second, but I don't know what happens with B yet, okay? So this is just to figure out A, which is usually, like I like to do them in order. You don't have to, but I'd like to do them in order. Now what I'm going to do is I need to look for the set of conditions, okay, where the concentration of B changes but A doesn't. Okay, so that's actually, so this is experiments 1 and 3 up here. And the experiments that we're looking for are experiments 1 and 2. B doubles, right? B goes from like 0. It goes here. So let me change my colors now so that I can. Let's see. I'll do, and I think this will show up okay. Blue. Yeah, that'll show up good. So I'm going to do reaction rate 2 over reaction rate 1. And that's going to be equal to, right? Let's see, 4.0 times 10 to the minus 5th divided by 4.0 times 10 to the minus 5th. Oh, by the way, I didn't write units here because they cancel out, okay? So then what'll happen is that's going to actually equal 1, but this is also equal to this. And then I'll show you how I get this. So B is 0.2 for experiment 2 and 0.10 for experiment 1, and that's to the nth power. So here we go. We're going to say this is equal to 1, right? Is equal to 2 to the n. And this should look familiar to you because, right? And I'm comparing these two and these two. Sorry, I meant to draw that in there. Because that means n must be 0. So what I know is that the rate law looks like this based on my data. Now, the output of this then is just that reaction rate is equal to K times A squared. When I left the brackets, I'll put them back in. So this is the easy way to do it. So let me explain to you what some of these things are. This, right, is the rate ratio. And this is the concentration ratio. And so the concentration ratio is always raised to an exponent that you need to find out. Now, we would say that this reaction is 0 order. And then I'll show you how that I got to that equation. 0 order in B, and second order in A, right? Overall second order. Oh, that's right. I'll do it like I did over. And so basically the overall order is just what you get when you add those two together. So if it had been 1 and 1, it would have still been 2, right? Or if it had been 1 and 0, it would have been first order overall. And then the orders are just the exponents. And so B not being dependent on concentration, the rate not being dependent on the concentration of B means that that one is 0 order. Okay, so good question is, where does this come from? Okay, so next slide, right? This was my proposed rate law here. Oh, pen's not working. Oh, there it goes. Proposed rate law. It's that the reaction rate is equal to K times A to the M and B to the N. And it could have been X and Y, but I find people are too stuck on X and Y and other letters need a chance, right? So, this is what I'm writing. Reaction rate. This is the general rate law is what it is. It includes all the cases. So reaction rate 3, right, is equal to K times A, right, to the M, and react times B. And you know what? I'm going to get rid of the brackets just to make it easier to write. To the M and then B to the N like this. But reaction rate 1, let's say, if this is what I was doing mathematically, is k times a to the m, right, and b to the n. Now this would be a3 and b3 and a1 and b1 like that. So the way we did this experiment, right, the way we did our calculations is actually we did this. We divided the two equations out because I didn't want to deal with this. And this is sort of a standard sciencey math trick. You divide constants out so you don't have to deal with them. And then you hopefully can come back and figure out what those constants are. In fact, that's what we're going to do with our other data here in just a second. And I have to show you some other math tricks as well. But we can divide that out. And so this is going to be equal to a3 to the m, b3 to the n, divided by, right, a1 to the m, and b1 to the m, like that. Now, or n, sorry. And then I'm going to do a little math magic. I'm going to separate those two and get them to be ratios of concentration. So the little math magic is I can do this. A3 over A1 to the m, because I pulled the exponent out, which you can do, times, then it's B3 to the over B1 to the n, like this. Okay, so now let's go back and look at experiments 3 and 1 and look at what the numbers were. Okay, so A3 is 0.2 and A1 was 0.1 and B was 0.1 in both. Okay, so in other words, and I'm looking right here, right? A in 1 was 0.1 and in 3 is 0.2. And we won't worry about this part over here for now, but we'll come back to that. And then it's 0.1 and 0.1. So what does this equation do when you have that, right? So what that means is this is going to be 0.200 molar like this, and 0.100 molar like that. This is all raised to the m power times, and then remember it was 0.100 molar for both. And then n here. And what happens? That cancels out. And now you have 1 to the n power, and then you don't have to worry about solving for n at the same time you're solving for m because you made it constant. Okay, and that's the reason why making one of those values, one of those concentrations, constant, is that it drops out of this equation and then it's easier to solve. Now, when we put the other side of the equation, there's R3 over R1, right? Then when we do that, then what we have is R3 over R1. That was equal to 16, I believe, 0.0 times 10 to the minus fifth molarity units per second divided by 4.0 times 10 to the minus fifth molarity units per second. Again, units cancel out, and now we're left with the number 4.0 is equal to this. Like that. Okay? And this is where we got to when we did, whoa, that was weird. This is where we got to when we did this. Okay? And what I did was made B go away by, in the experiment, this is part of experimental design, being able to hold one constant. Now, people can't always do that, right? So the analysis has to be more complicated at some level, but it's not here. So they can hold one of these constant, it goes away, and then you're only dealing with what's changing. That was the beauty of experiments 1 and 2 as well. In that case, A disappeared and B stayed, and we were able to calculate the order for B here because A went away. So really what we're dealing with, this isn't really N up here, that really should have been M. Or no, this one isn't N up here, it really should have been M, but I kind of just spaced out when I did it. So okay, hopefully that made some sense. Now there's a little bit more tragedy here that has to be talked about, and it's the math that you have to remember, because I know you know how to do it. If you're in this class, you've done this probably dozens of times, but it was dozens of times years ago. Okay, so let's deal with it. It's the use of logs to solve for exponents. So I have this equation. It looks like this: 4.0, right, is equal to 2 to the n. How do you get in? Well, in this case, we kind of just said, I chose an example where it was easy to see that it was 2. And oftentimes people will set up problems so that the answers are clear to see. But how do you solve it? The way you do it is you use logs. And you can either use base 10 logs or you can use natural logs. I'm a natural log kind of guy. So I will take the natural log of both sides. Like this, and the right hand side becomes this, because the exponent you can multiply it by, times, right, natural log, times the natural log of 2. And now you can solve it algebraically. N is equal to the natural log of 4.0, and this was actually, I think, 2.0 as well, but we'll just do it like it's natural log of 2. And then we can pull out my handy dandy calculator. The reason I say handy dandy calculator is if you were ever forced to watch Blue's Clues as a child. Yeah, that's what they say, you know, the handy dandy, and it was something. So we're going to take 4, and we're going to take the natural log of 4, which is on this calculator down here on the left, divided by, right, the natural log of 2, and I have to put the 2 and then the natural log, and then I'll hit equals, and that's equal to 2. Okay? So this is 2. Now, you could have done that. You could have solved that using some identities and stuff, and it would have been easy, but we're not doing that, okay? Right, so that's the idea. This is how you go about solving these problems when the ratios aren't pretty. If they're not 2 to 1, what is 1 1/4 to 1 or something like that? Then what do you do with that? You have to use this method of using logs to solve for it. And there's a little bit on the math review worksheet that we're doing, but mostly it's depending on you to remember how to do it. Okay. Okay, so what we need to do next, because we haven't done it yet, we haven't calculated the rate constant for this reaction yet. And so what we're going to do is we're going to calculate K, right, for this reaction. Here's the thing. There's 3 sets of data, and students often get confused, like, well, which one am I supposed to use? If they don't tell you which one to use any. Because remember, it's a constant. So it should be the same for every reaction, give or take a little bit of, experimental noise. Now, in this case, it's exactly the same. Generally, it's not exactly the same, but I'll show you how to do the calculation. So I know that the rate law, I've put it up here, is this, right? So I can say reaction rate, so that's going to be RR, right, is equal to K times A squared, and then I'm going to rearrange this because I want to find K. So I'll have K is equal to RR over A squared, and then I just plug numbers in. Now, well, let me just do it. So then I'll do experiment 1, that's 4.0, right, times 10 to the minus 5th, and the units are molarity per second. And here it's important that we put the units in because we're going to calculate something that needs to have units. So it's important that we put the units in. And so I'm going to divide that by 0.1, 00 times 10 to the minus, just 0.001 molar. But it's squared, right? So it's like this. So when I do that calculation, I need to move this control out of the way. I'll keep running into it. When I do that calculation, that'll come out to be 4.0 times 10 to the minus 5th molarity per second divided by 0.0100 molarity squared, okay? And then that'll come out to be 4.0 times 10 to the, I'm just doing the exponent math in my head. minus third. And then I'm going to end up with this funny unit, 1 over molarity times second. And this is typical of a second order rate law, wherever, it's second order overall, that you have molarity in the bottom because you're dividing by molarity here. That's the only way it can be, so that when you multiply it out, you get these units out as the answer. So when you're trying to figure out what the units are, really you just can put the units in and divide it out and see what the units come out to. That's what most people actually do. Instead of doing it all at the same time, they think about what the units will be, they do the calculation, and then they just write the units. Okay, so yeah, you could get the units for K simply by dividing molarity per second, which is what reaction rate is in, by the value for that, which would end up being molarity squared because it's a second order reactant. Okay. So I actually have a whole nother example in the slides that I'm not going to go over, but the answers are all worked out in the slides, and so you can go back through and do the calculations yourself. But I wanted to just sort of summarize what we're talking about. We've talked about order, right, and overall order, right? So if I have this reaction that's here, pointing at the wrong screen. The reaction that's here, and we have an experimentally determined rate law, right? The reactant orders are first order and half order. Okay, so reactants orders are first order in CHCl3. That's actually chloroform, and then half order in chlorine, like that. Overall, right, the reaction order, so the reactant orders, but the overall order, the reaction order, overall order is 1.5. All right. Just a couple of things to remember, right? Zero order reactants, if the concentration does not depend, if the reaction rate does not depend on the concentration, you know automatically that it's zero order. And you'll know that because it's a straight line, right? That is, it's not changing the slope as time progresses, and so you'll know it's zero order in that case. We're going to be doing a lot more stuff next week about this, but for now, this is what I want to go over. Now, rate constants, right? Rate constants are not concentration dependent, but reaction rates are. And what I mean by that is that we know that rate, right, is equal to K times and then something over here to something over to the exponent, right? This is the rate constant. The rate, reaction rate, is concentration dependent, but K is part of that same equation, so it's not concentration dependent. And you can sometimes have negative reaction orders. That means it actually goes faster as you remove it, okay? And that's actually mostly seen when we talk about something called product inhibition, where sometimes in the rate law you get something from the product that slows down the reaction. This is something that you see in biology a lot. It's a sort of homeostasis kind of thing. It's a way to maintain or self-regulate. And so some of these products will actually be part of the reaction, but in terms of not reactants and products, but in terms of, they are part of the products, but they're not in terms of like the reactants, but they're actually slowing the reaction down by being present in the solution where it's made. So anyways, you can have negative orders. We won't see any in this class. I'm just telling you, when you like move on and become a biochemist or something, or do biology and do a little kinetics there, maybe you might see like the order is negative or overall negative because it's an inhibitor of a reaction. Okay, so that's the summary of this week's unit, and next week we'll finish this chapter.